My name is Charles Cosette. On behalf of my colleagues at McGill University and Polytechnique Montréal, I'm presenting our work on optimal multi-robot formations for relative pose estimation using range measurements. Our long-term research project has a large emphasis on ultra-wideband radio, which is a type of radio technology that can be used to produce 10-centimeter accurate distance measurements between any two transceivers. One of our custom UWB modules can be seen mounted to a quadcopter leg on the top right photo. UWB radio is cheap, lightweight, small, has low power consumption, and is also capable of data transfer. This makes it an attractive option for mobile robotics, especially those with limited computational resources. In our work, we install multiple UWB tags on each robot so that the relative position and heading can be estimated from distance measurements directly. Towards this goal, we flew our quadcopters under a motion capture system and collected UWB measurements amongst other sensor measurements. On this dataset, we ran an extended Kalman filter to estimate the relative poses and produce the plots on the right. Notice the time-varying confidence bounds. It turns out that the motion of the robots and the formation geometry has a significant effect on filter covariance. In other words, estimation accuracy is dependent on the formation geometry, and we may therefore ask what formations are optimal in terms of minimizing estimation errors. Let's now model an example problem with three agents. We use pose transformation matrices to represent relative poses, which belong to the special Euclidean group of dimension n. Arbitrarily taking robot 1's point of view, the full problem state consists of relative poses of the other two robots. We will then assume that all the range measurements between the robots can be written as a function g of this state as corrupted by additive Gaussian noise. For states that belong to a manifold, which is the case when using pose matrices, it is necessary to define a perturbation operation that modifies the value of x given an update vector psi. We use the standard exponential map from Lie group theory. We can now identify an on-manifold approximation to something called the Fisher information matrix. The inverse of this matrix determines something called the Cramer-Rao bound and represents the lowest possible covariance achievable by any unbiased estimator. We use this as a basis to construct the cost function to be minimized. Minimizing this function aims to make the Cramer-Rao bound as small as possible by equivalently maximizing Fisher information. These plots below show the value of the cost for varying agent position. On the left plot, the position of the blue agent is being varied and the cost plotted. On the right plot, the position of the top right agent is being varied and the cost is plotted. Notice that, on the left plot, we see a yellow line of very high cost. This corresponds exactly to when all the tags would line up, which is very much the expected result and the desired behavior. In the three-agent scenario, we can also see that the cost is going to be largest when the agents are near the straight line formation. It turns out that minimizing this cost alone will yield formations that are unacceptably close to each other. So we add a collision penalty term to our cost function to avoid this. This penalty is a simple function that blows up when the distance between the agents approaches some chosen safety radius. We finally iterate the robot state with an on-manifold gradient descent procedure. This allows us to smoothly iterate over the robot attitudes in addition to positions, all while avoiding singularities and wraparound associated with angle parameterizations. With the framework presented in our paper, we can compute optimal formations for an arbitrary number of robots, an arbitrary, potentially sparse measurement graph, which is to say that maybe not all pairs of transceivers receive distance measurements, as well as 2D and 3D problems. To test these results, We examine the performance of a simple least squares based relative pose estimator. The covariance reported by the estimator is shown as a blue ellipsoids. In a straight line, the covariance is very large and erratic, and so is our proposed cost function shown in the top right plot. However, when the agents move into their optimal triangular formation, we can see that the covariance estimation errors and cost function all reduce significantly. This is evidence that the cost function is a good quantification of the formation geometry dependent estimation variance. To summarize, we propose a function that accurately characterizes the formation geometry dependent estimation variance. We use an on-manifold gradient descent procedure to optimize this function. We also show improvements on real estate estimators. In terms of future work, we see it as very feasible to modify the cost function to incorporate prior information about the state. But perhaps more interestingly, we would like to use this cost as an inequality constraint on some other planning objective. For example, find an indoor trajectory for the robot team that always maintains the estimation cost below a specific threshold. Thanks for watching. I welcome you to contact us anytime if you're interested in discussing.